Now she says it's being recorded, so that's good. So let me get started all over again on the second lecture. So before we move into the quantum field theory, I reviewed the basics of the Lagrangian and Hamiltonian and quantum mechanics derived from them. So what I said was that the Lagrangian is taken as the starting point of discussion of any physical systems. And the one reason is that Hamiltonian can be used as a beginning too, but when you get to Lorentz invariant theories, Hamiltonian is actually not Lorentz invariant, but Lagrangian is. So to discuss symmetries, typically Lagrangian is better. And that's why we take Lagrangian as the fundamental starting point for discussions. Hamiltonian is actually a derived quantity out of it. And also a canonical quantization condition is also derived from the Lagrangian. So Lagrangian knows all of these things in it. So that's why Lagrangian is a good starting point for discussing any physical system. So that's why we would like to do it. And the next thing we did is to go to the basics of how that works. So we start with the action of any system that's given as a time integral of the Lagrangian. Lagrangian is a function of coordinate and its time derivative. And by differentiating Lagrangian with the time derivative of the coordinate, that defines the canonically conjugate momentum, pi. And using this, we do the Legendre transform so that Hamiltonian is written as pq dot minus L. And you eliminate the time derivative of the coordinate in favor of the momentum and rewrite the Hamiltonian as a function of coordinate and its conjugate momentum. So that's what Hamiltonian is. And at the same time, Lagrangian tells you that given this definition of the canonically conjugate momentum, you're supposed to use this canonical commutation relation. So that's always the beginning of the quantization process for any physical systems. And we immediately jumped into an example of harmonic oscillator. And so Lagrangian is given by kinetic energy minus potential energy. By following this definition of the canonical momentum, we find that pi is mx dot. Sounds very conventional expression. And then Hamiltonian is then defined by px dot minus L. And you eliminate x dot in favor of p. And just by doing a little algebra, you find the familiar expression that the Hamiltonian for harmonic oscillator is p squared over 2m plus half m omega squared x squared. And of course, that comes with this canonical commutation relation, xp being ih bar delta ij. So that's how the quantization works. And once you have Hamiltonian and canonical commutation relation, then you can immediately write down the Schrodinger equation on any physical state ket psi. So ket is a function of time, and time derivative of the state is given by the Hamiltonian acting on the state. And I didn't say this on Wednesday, but this is actually a very interesting fact, namely that Hamiltonian is a very special operator that moves time forward, because acting Hamiltonian state means it actually goes a notch in the positive time direction. That's what the Schrodinger equation says, right? So Hamiltonian is a very special operator that moves time forward. And once you have this canonical commutation relation between Q and P, you know that you can go to position space or coordinate space representation or momentum space representation of any states. And if you choose the coordinate space representation, momentum operator is given in terms of the derivative acting on a coordinate, h bar over I del del q. So by defining this wave function to be the coordinate representation of the state, then you can derive the time derivative of that state. And the time derivative is given in terms of ih bar times Hamiltonian acting on it. And I see now there's a typo here. I apologize. I'm going to fix this when I post the slides on the B courses. So this is supposed to be h in the middle. So you can just forget about this part here. And the h acting in the middle means that q operator becomes q eigenvalue. So now q is a number. And p operator becomes this q derivative. So Hamiltonian is now written in terms of q and derivative acting on this wave function psi over q and t. And that's something you have done a lot in the quantum mechanics class, namely that when Hamiltonian is given by this as an example of harmonic oscillator again, then Hamiltonian of x and p is now written using the derivative with respect to x here. So that's the first term. And second term used to be x operator, but now acting on a position space, this becomes x number as an eigenvalue of the position operator. So the Schrodinger equation ends up looking like this. You have a wave function psi of x and t. Its time derivative is given by the second order derivative with respect to the position. So that's the Schrodinger equation we have done all along in quantum mechanics class. And one thing that's special about Hamiltonian is that because it moves time forward, at the level of this, the formal expression using this ket, abstract ket, you can formally integrate this right away and write the solution that's given by this operator e to the minus I ht over h bar acting on the initial state at time 0. So you can see this right away that taking time derivative of this expression, you bring Hamiltonian down from the exponent that's acting on state itself, hence recovers this original Schrodinger equation. So if you write this formal solution to the Schrodinger equation using this time evolution operator, that's this yellow thing in between, we often use this time evolution operator to write explicit solution to the Schrodinger equation, and we're going to actually use this later on when we discuss more about the harmonic oscillator. So this is one little bit I hadn't discussed on Wednesday. Now I'm adding it here. So Hamiltonian is special because that moves the time forward. And the way Hamiltonian moves time forward can formally be given by this exponential unitary operator, which is called the time evolution operator for obvious reasons. So I'm adding this extra bit to what we discussed on Wednesday. But as you all, of course, know, Hamiltonian is special for another reason, because Hamiltonian is nothing but the energy. So when you have this Schrodinger equation derived from the previous slide, now that you can look for energy eigenstate, that Hamiltonian has an eigenvalue E, then you can solve this equation, which is now time independent. So that's a lot easier to solve. And then once you see this equation, I wouldn't be able to tell right away what the solution is. I have to look up something. So in this case, it's given by this Hermite polynomials, and I don't remember them, but nonetheless, this is the solution given in the textbooks. So that's how you know that this is the solution to this eigenvalue equation for the Hamiltonian, and the eigenvalue does come out to be this familiar h bar omega times n plus 1/2, where n is a non-negative integer. So you have all seen this in quantum mechanics class. And one sort of a thing which is difficult for me is that I can never remember these orthogonal polynomials. Thanks to Dirac, though, we know how to solve this without ever knowing what these orthogonal polynomials are. And I'm sure this is what you have seen in the quantum mechanics class too, by using what is called the creation and annihilation operators. So Dirac was such a genius that he told us, you don't need to remember these orthogonal polynomials, you can work it out. So the idea is that once you have this Hamiltonian given by basically p squared plus x squared, just like any number given by one number squared and another number squared, you can write it as a square of a complex number. So if it is a squared plus b squared, that can be written as a plus ib times a minus ib, right? So any square, the sum of the two squares can be written as an absolute square of a complex number. So that's the beginning of this idea. So this is actually correct at the level of the classical mechanics, but it's not quite correct at the level of the quantum mechanics, because here we treated x and p as if they are just pure numbers, but they aren't, they are actually operators. So I'm sure you have done this already in quantum mechanics class. I will be asking you this just once again to refresh your memory in the homework problem I'm going to post later today. So if you pay careful attention to the fact that x and p do not commute, you have to be very careful about the ordering between x and p, because the commutator is given by IH bar. This is not quite right. There's a little bit of correction to this. That turns out to be this half h bar omega. And you recognize this as a 0-point energy for the harmonic oscillator. So by paying careful attention to the ordering between x and p, you can write this out in this form. And then you define this left-hand side of the operator as what is called the creation operator, given by this square root m omega of 2h bar x plus ip over square root 2m h bar omega, by factoring out the factor of square root h bar omega out of this expression on the left. And I do the same also on the expression on the right. So that's just the Hermitian conjugate of a dagger we just introduced. So a dagger is a itself, and the only change here is the I now changes to minus I. So now I have both a dagger and a here. And using them, I can write Hamiltonian in much more simpler form of h bar omega now factored out. That's the only quantity that has dimension of energy now. And a dagger dimensionless. So this first operator turns into a dagger times square root h bar omega. Second operator turns into a times square root of h bar omega. Two square roots now multiply to h bar omega. And then I'm left with this 1/2 when I had to pay careful attention to the ordering between x and p. So you have seen this in quantum mechanics class already. So, and also one thing we need to derive about the properties of A and A dagger to work out this commutation relation between them. So by knowing X and P commutation relation, that XP commutated IH bar, you can easily work out what the commutator between A and A dagger is. And that turns out to be just simply 1. So again, you have all seen this. And you call this A dagger as the creation operator. You call this A as annihilation operator. And I know some books call them with different names, raising operator and lowering operator, but in most books I'm aware of, they are called creation operator and annihilation operator. So that's something you have seen, I believe, in quantum mechanics class. Now comes a little quiz to you. How come that this operator is called a creation operator? And I hope the polling works this time. So why the name creation operator? So multiple choice. And this doesn't count to your grade, so you can choose whatever choice you like to take. Okay, first choice. To pay respect to Dirac's creativity. That's why this is called creation operator. Second, this creation operator can actually create particles. Third, that's because of Dirac's religious views on creation. So, okay, let me launch my poll. And hopefully this works. And cast your ballot. Okay, it's working this time. Good, good. I'm getting the ballots. 48% now. 68%, 80%. Oh, this is fun. Okay. 22 of 25. I think this is it because the 25 includes myself, my iPad, and the Reggie. Okay, so let me end poll and share results. Can you see the results? Yes? Okay, good. All right, so the second choice got the majority votes, and I would say that's the right answer. And we will see later on how it can actually create particles when we discuss the quantum field theory. And that's why the harmonic oscillator is actually a very important thing for the later discussions. So this creation operator actually ends up being an operator that can literally create a particle, and that's how we actually use it in the context of quantum field theory. Okay, so that's it for this quiz for now. All right, so now we have creation and annihilation operators. And using this creation annihilation operator, we can also derive energy levels and ground state wave functions actually much easier compared to what we used to do with the Schrodinger equation. So we got this Hamiltonian, and let's take the expectation value of the Hamiltonian for some arbitrary state. And just by plugging in this expression of the Hamiltonian into this expectation value, this 1/2 h bar omega is just a number, so that just returns a number. What's non-trivial is this A dagger A operator. So I factor out h bar omega to the front. A dagger A is sandwiched between the state ket and bra. But this combination is A acting on psi, and Hermitian conjugate of this A acting on psi is exactly this psi bar with A dagger acting on it. So this whole thing, A dagger A expectation value, is nothing but absolute squared or norm of the state A acting on psi. And clearly, this is the absolute value of the state. So this is positive semi-definite. I have an additional number here. So this expectation value, the Hamiltonian, is bounded from below. The lowest it can possibly be is this constant b's. It can't be smaller than that. And you can saturate this inequality only when this first term vanishes, which means that minimum energy is obtained when the annihilation operator would annihilate, literally, that state. So this is how we know what the condition is on the ground state. So we didn't have to solve any second-order differential equation to obtain this result. Minimum energy is 1/2 h bar omega, and ground state is obtained by this condition. That's why this is actually a lot easier to deal with. And recalling that the annihilation operator is given by this expression, now we can obtain a condition on what the wave function for the ground state should look like. So when I take, again, the position representation of this condition that A acting on ground state should vanish, I rewrite this annihilation operator in terms of x as a number now, and p as a derivative operator acting on this wave function x0. This is the first order differential equation. That's a lot easier than second order differential equation. And then you can readily solve this. By acting x derivative, returns basically x. So then the wave function should be exponential of the x squared. So by cleaning up this differential equation, by eliminating this coefficient of d over ddx, and put that into the first term, x derivative should give you m omega of h bar times x. What that means is that the wave function should be given by exponential of negative m omega squared x squared of 2h bar, so that x derivative will pull out x squared derivative, which is 2x. 2 cancels 2 downstairs, so that exactly give you m omega over h bar. And I made a typo here. There shouldn't have been this squared on omega squared. Again, I'm going to fix this after class before posting the slides on B courses. So basically, without knowing anything about Hermite polynomials and stuff like this, you can obtain the ground state wave function just by looking at this condition that ground state cannot be lowered anymore because by this annihilation operator. So this is really ingenious on Dirac's part, so that you can obtain this ground state wave function without knowing anything about these orthogonal polynomials. And that's great for me as well. So this is how you get the ground state. And we also define this number operator, which is just A dagger A, to simplify this expression of the Hamiltonian. It's just now n plus 1/2 times h bar omega. So we're going to use this to also understand excited states as well. So number operator is this. Hamiltonian is now given in terms of this number operator, just as I said on the previous slide. And then comes A and A dagger commutation relation. So in the end, this is all you need to know to get this entire spectrum of the excited states. So the idea is that NA commutation relation gives you minus A. That means A would lower the eigenvalue of N, and we'll see how that works in a moment. So let's first work out this NA commutator. And because N is given by N dagger A dagger A by definition, in order to get this commutator, you need to find out what doesn't commute with A on the right-hand side. And of course, A commutes with itself, so that disappears. So the only thing that remains is A dagger not commuting with A. And we know already A dagger A commutator is 1. So the A dagger A commutator then is the opposite from A dagger commutator. So this commutator is then -1. And as an end result, NA commutation relation is -A. So you have seen this already in quantum mechanics class, I believe. And the similar thing, I can work out the commutation relation with N and A dagger. So in this case, what doesn't commute in here is this A part of N that has commutated with A dagger. So in this case, I get this A dagger commutated right away, not the negative of it. So this is just 1. So this is positive A dagger. And that ends up meaning that A dagger is capable of making N bigger by 1. So let us check that. So first take a state, which is an eigenstate of this number operator N, with the eigenvalue little n. At this stage, we may not necessarily know that this little n is an integer, so we are going to find this out. So if you actually act this A operator, annihilation operator on this N state, you can use this commutator to rewrite it. So in this case, this is NA acting on state N, and NA operator can be written as NA minus AN plus AN. So I haven't changed anything here. So NA commutator is NA minus AN cancels this plus AN. So the whole thing is just back to NA. So nothing has been changed. But writing it this way is very useful because now N operator is acting directly on N state that pulls out this N eigenvalue. NA commutator is something we worked out above here. That's negative A. And putting these things together, then I can combine this to NA times N minus 1. So now I see that N operator acting on state A acting on A returns the eigenvalue N minus 1. So now I know that after acting annihilation operator on N state, basically gives you number state with N minus 1 as its eigenvalue. But it's not quite correct that A acting on N is N minus 1 state precisely because it's not normalized correctly. So that's something you can work out very easily. This state, A acting on N, I can compute its norm by taking Hermitian conjugate of this, that turns into N and A dagger, and the original state. And then A dagger N in between is nothing but the number operator. So acting that on the number state N, that returns the eigenvalue N. So this is the way you can easily work out the norm of this state. So to properly normalize it, I need to factor this out by a square root of this norm. So that's why this state, A acting on N, is N minus 1 state. We know its eigenvalue from there, but together with the additional normalization factor of the square root N. So without knowing anything about differential the equation, we know how these states can be obtained. And we do the same thing also for A dagger N. You go through the same algebra using commutation relation. You'll find that A dagger N is now an eigenstate of N with the eigenvalue N plus 1. That's why A dagger now makes the eigenvalue a notch higher by 1. And we again can compute its norm, and that turns out to be N plus 1. So A dagger acting on N state gives you the state with N plus 1 together with this extra normalization factor of square root N plus 1. So I believe you have all seen this before, but let me pause here if there are any questions. Is everything okay? Okay, some people are nodding. It's great to have this visual feedback. Okay, so then let me move on. So now we know that we can get this entire set of states, starting with the ground state and all the other excited states using this creation and annihilation operators. So using what we have found on the previous slide, so acting A dagger on a state, you get the next state with this normalization factor. So that's this step here, going from state n to n plus 1, together with this normalization factor, square root of n plus 1. So what that means is that I could have started with a level 1 down from n minus 1 by acting a dagger on n minus 1 state. I get this state n with the normalization factor square root of n. And I can keep doing this. So I can act this a dagger on state 3 to get to state 4 with the normalization factor of square root 4, 2 to 3 with this normalization factor square root 3, 1 to 2 with this normalization factor square root 2, and finally from 0 to 1 with a normalization factor square root 1. So we learn that state n can be obtained by acting a dagger on the ground state 0 n times, which gives you the normalization factor of square root 1 times 2 times 3 plus times 4 times dot 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 times n. That's nothing but the n factorial. So by acting a dagger n times on the ground state, I get the state n with the normalization factor of square root n factorial. So I dividing the both sides by square root n factorial. Now I know how state n is defined using this creation operator acting on the ground state n times together with this normalization factor. So what that means is that we know a dagger can be written as x and x derivative. We have worked out what the ground state wave function is with a Gaussian form. So I can just literally use this differential operator n times to work out the wave function of any state with any n without knowing anything about this orthogonal polynomials. So that's great. You know, I don't have to carry this thick book of all the orthogonal polynomials when I travel. I just use the same differential operator n times to get any state wave function anytime I want on a piece of paper. So that's really the ingenious thing what Dirac invented. So we do want to pay actually respect to his creativity. At the same time, we also know that using annihilation operator, you can go down one notch. So that's exactly what this annihilation operator does, all the way from state n plus 1 all down to the ground state. So we can always go up and down any way you want, and we know exactly what happens. So that's what we are going to actually use very heavily when we talk about quantum field theory. Okay, any questions about that slide? Everything okay? Good. And this is the thing you probably have not seen. Now that we find this creation and annihilation operator so useful, it's a lot easier if we start with them. So we used to write the Lagrangian of the harmonic oscillator this way, and this is the familiar expression, kinetic energy minus potential energy. But we know how to rewrite it with P and X, first of all, because we have derived this Hamiltonian as a function of P and X. And the relationship between L and H are by this Lagrangian transform. So let us use this backwards to write the Lagrangian using A and A dagger by following steps. First of all, I write L by using this Lagrangian transform backwards as peak x dot minus h. Okay? And then I rewrite x dot in favor of p because it's nothing but p over m. So then px dot minus h is p times p over m minus Hamiltonian. And that actually turns into basically the p squared over 2m minus half m omega squared x squared. And now that Lagrangian is written in terms of x and p, I can rewrite x basically as a dagger plus a times some normalization factor. A dagger times a plus a cancels this p part in it. So that's how I can rewrite x. I can also rewrite p using a dagger minus a, because that cancels the x part of it. So that's how I end up with this expression. So this px dot is this, and this is h. And I expand this out, and then many things start to cancel. So I get this part to be a minus a dagger times a dot plus a dot dagger. Remember, this dot comes from this x dot. And once you come to this expression, of course, this half is just a constant we don't care much about. And also, you can drastically simplify this first part of the Lagrangian by dropping pieces that are total time derivatives. Because the part of the Lagrangian that's a total derivative doesn't do much, because that's only given by the boundary surface terms. For example, it doesn't change the Lagrange equation when you derive it from a Lagrangian. So most of the time, we don't care about the total derivative terms in the Lagrangian. So by dropping them, you can simplify this expression to something that looks like this. IH bar, A dagger, A dot. That comes from this first term by dropping total derivatives. For example, if you look at the piece A times A dot, that's the time derivative of A squared, right? If you take time derivative of A squared, you get A times A dot. That's why it's the total derivative, and I drop it. Same goes with A dagger and A dagger dot. It's a total time derivative of A dagger squared, so I'm going to drop it. A dagger A dot is the piece I have here, but only half of it. I also have A dot dagger. But then I can use total derivative of A dagger, basically do integration by parts to turn A dot dagger to A dot A dagger, so that I end up with this form at the end of the day. So by dropping constants and total derivatives, I arrived at this form of IH bar A dagger A dot minus H bar omega A dagger A. And this is the form we're going to use a lot when we get to quantum field theory. So this may look a little bit odd because we rewrote the Lagrangian of the harmonic oscillator using creation and annihilation operators, but this is the way that's actually most easy to deal with. So if you take this Lagrangian as a starting point, then the canonical commutation relation is simply that A is the coordinate, IH bar A dagger is momentum, and its commutator is IH bar, and therefore A dagger commutator is IH bar. So you get that commutation relation right away from this. And also, when you take Lagrange transform starting from this, you take PQ dot, which is nothing but this one, minus L to become the Hamiltonian. Then you see this H bar omega A dagger A is the Hamiltonian right away. No algebra needed. So you get this H bar omega times the number operator as a Hamiltonian in just one step from this Lagrangian. So that's why this form of the Lagrangian is the easiest one to use when you rely heavily on the creation and annihilation operators. So that's why I'm going to use this form a lot from this point on. Okay, so this is probably something you have not seen before. So let me pause again to see if there are any questions.
Yes, I have two questions. The first one is you just say A times A dagger. Sorry, A times A dot is the total derivative of A squared. But what if A and A dot they don't commute? So you have like if you take the time derivative of A squared.
Yeah, that's an excellent question. Yeah, that's an excellent question. So if you pay attention to ordering between A and A dot or A and A dagger, then there would be additional terms. But those additional terms end up again being just constants. So I glossed it over. So, I tried to save my time and glossed it over, but you caught me. So it's clear that this is a very smart class. But if you actually pay careful attention to this, A dot, if you solve the equation of motion, turns into minus I omega A. So between A and A dot, both of them actually turns out to be A. So there, I don't need to really worry about ordering between them. The same goes with A dagger and A dot dagger. And if you solve the equation of motion, A dot dagger is I omega times A dagger. So A dagger and A dagger dot, again, commute with each other because both of them are A dagger. What doesn't commute, and that's where I cheated, is between A dagger and A dot, or A and A dagger dot. So when I did the integration by parts to move this time derivative acting on A dagger to time derivative acting on A instead, then I have A dot, A dagger, not A dagger, A dot. And these things don't commute. So when I change the order between them to put them all into this form of A dagger, A dot, I cheated there, and that leaves the constant term. But all I have done is to commute A and I omega A dagger. And A dagger commutator is 1. It's just a number. So in the end, the piece I glossed over turns out to be also just a constant. And that's included in this piece of a constant. So you're right. I cheated. I glossed it over. I hid these things under the rug. But what I hid under the rug is all contained in this constant piece. So end result is still correct.
Okay.
So I hope that makes you happy.
Okay, yeah. And I just came up with a comment because you keep talking about like first term and second term, and I cannot see the pointer, so sometimes
you cannot see the pointer. I'm sorry. Why is that? Again, that's something I need to learn about Zoom. Maybe, no, not here. How do I do this? Go to Zoom. No, I'm not finding that either. I see, you do not see my pointer.
Yeah. So you keep talking about these slides, then it's sometimes cannot like it keeps saying like bad. Dagger, dot, and
okay.
And also I have another question that is
okay. Maybe I apologize. I will try to figure out how to actually use a pointer on this.
Oh yeah, never mind. And yeah, you want to use like A dagger and A to write the Lagrangian. So you use you substitute X dot directly from the dot of A and dagger. What if I multiply a M, that is M P X dot, and divided by M? So I have P squared over M. Then I can just use the normal A and A dagger instead of their time derivatives. And do I have the same result that finally?
Yes, you end up with the same result, but only up to the equation of motion. So only to the extent that you always keep A dot to be minus I omega A, then you get the same answer. But this form is preferred because this is the form that tells you that A and A dagger are canonically conjugate to each other. If you had used the equation of motion to eliminate A dot and write it as minus I omega A, I lose time derivative in Lagrangian completely, then I don't know what is the correct canonically conjugate variable for A anymore. Keeping this form that L is Px dot minus H had a secret in it, namely that it has X dot in a way that X dot, what multiplies X dot is indeed P. So it's better to keep this structure that you have P times X dot inside the Lagrangian. And that ends up this piece in this cyan, which is a very useful thing to use because it knows both about canonical commutation relation between A and A dagger, and also about the Hamiltonian, which is nothing but H bar omega A dagger A. So that's why this is the useful expression we always use for the later purposes.
Okay, I see.
Does that answer your question?
Thank you.
Okay.
Yes, yes.
And thanks for telling me that you are not seeing my pointer, which is a big problem now. So I tried to speak
yeah, I don't know if
every
it's
pieces.
yeah, I don't know if it's my problem with
I doubt it. I'm sure everyone's seeing the same thing. Maybe other people can either say something about whether you see the pointer or not.
Yeah, we can't see your pointer.
See it.
Okay. Thank you for letting me know. Yeah, Elijah says same too by chat. Okay, yeah. So I need to figure out how to do this. And sorry, I don't think I can do it today. Hopefully, I know how to do it on next Wednesday. Okay, but anyway, any further questions on this slide? Because we keep using this expression. Okay, Sahil.
Yeah, why can we, I guess, not regard the total derivatives in this final expression?
Yeah, so at least in the classical mechanics, all you care about is the Euler-Lagrange equation, right? And actually, I'm kind of surprised why people came up with this idea of Lagrangian Hamiltonian in classical mechanics, because that's not really necessary for the purpose of doing any Newtonian mechanics by solving F equal ma. But for some reason, the ancients in the 18th and 19th century decided that rewriting Newtonian mechanics using Lagrangian Hamiltonian was a good thing. And when you do so, to the extent the only thing you care about is the equation of motion, namely the Euler-Lagrange equation, total derivative term in the Lagrangian does not affect the Euler-Lagrange equation. Because as you might remember, the Euler-Lagrange equation is obtained by taking the variation of the action. And so the action is written as the time derivative of the Lagrangian. I hope you can see this.
Yeah.
Okay. And then you take the variation. And because L is a function of both Q and Q dot, you get this. And then you use the integration by parts to make this dot act on the first term. Plus the surface term between initial and final time. And keeping the boundaries fixed, you demand the thing inside has to be 0. And that's the way you get the Euler-Lagrange equation. And if you don't remember this very well, I posted the lecture notes on classical mechanics on B courses, classical1.pdf. So I encourage to look at that to just refresh your memory about Euler-Lagrange equation. But now imagine that you add a total derivative term to the Lagrangian. Then this term can be integrated right away to a surface term. So it doesn't depend on how much variation you do in the intervening time period, because it depends only on the surface, initial condition and final condition. So this ends up being this just additional term to the surface term. But because you keep everything fixed at the initial and final time, nothing really changes. Euler-Lagrange equation is still the same. So adding a total time derivative to the Lagrangian is not going to change anything about the Euler-Lagrange equation. That's why we don't care about the surface terms or the total derivative terms in Lagrangian. Having said that, though, this is a statement that's true strictly in classical mechanics. When you do quantum mechanics, then this surface term matters to some extent, because when you add this additional surface term to Lagrangian, correspondingly, you have to change the phase of the wave function by e to the minus I o over h bar. But again, this doesn't matter for most purposes because if you change the phase of the wave function, and when you compute the probability, you take absolute squared and phase disappears again. So having this phase change, which does appear in quantum mechanics, so you have to be just a little bit more careful compared to the classical mechanics when you freely throw away total time derivatives. You need to change the phase convention or wave function when you throw away total derivative. But that's all that takes. So when you have thrown away the total time derivatives from your Lagrangian, which we did in the case of a harmonic oscillator, and that have changed the phase convention of the wave functions, but then you start anew with the Lagrangian, where you have already removed the total time derivative, and then start building your wave functions from that. So then you have already changed your phase convention you don't care about, and then you can build the entire set of states using the new Lagrangian. So as long as you consistently use the same Lagrangian throughout your calculations, then you don't have to worry about this phase convention either, because you have fixed convention throughout your calculations. So that's an excellent question. Again, you spotted what I glossed over, but this is the answer. So first, in classical mechanics, all you care about is the Lagrange equation. Therefore, total time derivative really doesn't matter. In quantum mechanics, it matters a little bit because when you throw away total time derivative, you have to change the phase convention of your wave functions. But as long as you stick with the Lagrangian after throwing away time derivatives, then you no longer change your conventions. So as long as you stick with the convention, you are totally okay. So either way, in classical mechanics or quantum mechanics, you can throw away total time derivatives. You have to be just a little bit more careful in quantum mechanics, but it all has to do with just the phase convention. Does that answer your question, Sahil?
Yeah, that does. Thanks.
Oh, okay. Any further questions? Okay. So just in case you are a little bit more curious to know about this, the phase convention stuff, taking this total time derivative away really has to do with what is called a unitary transformation. And as you can see, this thing is really a unitary operator acting on the wave function, right? The phase is unitary. So there is this connection between any unitary transformation you might do on your state, like translation, rotation, and various other things, have to do with the total time derivative in the Lagrangian, just in case you are a bit more curious about it. And I think I have put in that discussion in the lecture notes on classical mechanics, but if I hadn't, then I tried to add that in for those of you who want to have a little bit more advanced knowledge about this business. And so you will see that in lecture notes. If I have to do an update, I will do it. Okay. All right, now back to the slides. So this is what I finished. So I end up using this form of the Lagrangian a lot from this point on. So this was the case with a single harmonic oscillator. And suppose you have several of them. If you have multiple harmonic oscillators, all you have to do is just add Lagrangian for each of the harmonic oscillator, and that's the total Lagrangian. And make sure that at this point, these harmonic oscillators are totally independent from each other, namely they don't interact with each other. So this is just a collection of independent harmonic oscillators. So in that case, all you have to do is just add up Lagrangian for each of the harmonic oscillators, So this is what you would do with the standard expression for the Lagrangian. And Hamiltonian is also added together. And commutation relation is also generalized. And A and A dagger that belong to different harmonic oscillator don't care about each other, and therefore they commute. Only when you take the commutator of A and A dagger for the same harmonic oscillator, they return 1, namely they do not commute. So that's very easy to remember. And all of them are derived from the same Lagrangian as we talked about, namely that you just add this form of the Lagrangian written in terms of A and A dagger for each of the harmonic oscillator, and you just add them up. And from this Lagrangian, you see immediately that the conjugate momentum for AI is A dagger I, specifically the same I, not other A dagger, J. So this way you can see right away that A and A dagger do not commute and give you 1 only when they belong to the same harmonic oscillator. And then also at the same time, you see right away that Lagrangian is PQ minus H. So H is definitely the second term in the parentheses. Now that I don't have a pointer, I have to speak out the second term in the parentheses, and that's the Hamiltonian. So Hamiltonian is just the sum of H bar omega I, AI dagger AI, once I drop the constant term in it. And then you can build anti-Hilbert space. So the ground state 0 is a state that is annihilated by every one of these annihilation operators AI. So A1 acting on 0 is 0, A2 acting on 0 is 0, AN acting on 0 is 0. So this ground state is annihilated by every annihilation operator. And starting from that state, I start acting A dagger on it. And I can act A dagger for any one of them. I can act a I dagger on it, I can act a 2 dagger on it, and so on and so forth. So that's how you can start building the entire Hilbert space from that. And again, remember that A daggers commute with each other because they are all canonical momenta belonging to different harmonic oscillators. So when you act A dagger on the ground state to build up the excited states, it doesn't matter in which order you act A daggers on the ground state. So the example of the third state, AI dagger, AJ dagger acting on ground state, again, I have to speak because I don't have a pointer. It doesn't matter whether you act AI dagger first or AJ dagger first because they commute with each other. On the fourth state with 3 creation operators, I have I, J, and K. Again, it doesn't matter in which order I act them on the ground state. Given 3 operators, I have 3 factorial ways of acting them. So there are 6 ways, but all 6 ways give you identical results because they commute with each other. Namely, acting 3 creation operators on the ground state give you a state that is symmetric under the interchange of I, J, and K. And that actually turns out to be an important property of these creation operators. In whatever order you act the creation operators in the ground state, the order doesn't matter because they commute, and is automatically symmetric under the interchange among different creation operators. It turns out that is the key where quantum field theory connects to quantum statistics. The states you get by creation operators are automatically symmetric under the interchange. And that's nothing but Bose statistics of identical particles. When you interchange 2 different particles, as you correctly guessed with a quiz, A dagger does create a particle. So when you interchange the order of 2 creation operators, you are interchanging 2 particles. But the state doesn't change. It's already symmetric, which is the condition for identical bosons, as you have seen in quantum mechanics class. So this is where you start seeing the connection between using creation annihilation operator, which we do all the time in quantum field theory, to the property of quantum statistics, where your state is required to be symmetric under the interchange of particles. So far, I'm talking about just pure harmonic oscillators, but we will talk about actually using this as a creation operator for particles next. Then this property that different A daggers commute with each other end up being the property, the state you get is automatically symmetric under the interchange of particles that are identical bosons. Okay, so we will come back and talk about this symmetrization when we talk about creating particles next. But anyway, any questions at this stage of this multiple harmonic oscillators? Somebody speaking. Mirel? Okay.
Yes, hi. Just because you brought up the Bose-Einstein statistics, I was wondering, so if we were doing this with fermions, would the A daggers no longer commute? Would they, like, because it would have to be anti-symmetric, so how would that manifest with these operators?
That's an excellent question. Again, you spotted what I glossed over. So in the case of fermions, you're completely right, Mirel, that when you interchange two particles, you're supposed to get -1. It has to be totally antisymmetric. So what that means is the canonical commutation relation I used, namely that A and A dagger has commutator 1, A and A commute, A dagger and A dagger commute, don't quite work for fermions. I have to change that. It turns out that there's a simple change you can do, and I wanted to come back and talk about it actually maybe in 2 lectures, not today, but anyway, now that you brought this up. So the change is very simple. We know the commutator between A and B operator is AB minus BA, right? That's the commutator. You change this minus sign to plus sign. You change this commutator to AB plus BA. And that is called anti-commutator. If you do that, when A and B anti-commutator vanishes, that's what we expect to have between 2 creation operators. They no longer commute, but they anti-commute, namely A dagger A dagger J plus A dagger J, A dagger A is 0. So if you move one piece to the other side of the equation, you find A dagger I, A dagger J equals to negative A dagger J, A dagger I. And that's the minus sign you want. So this is how you can get also fermion antisymmetric wave functions automatically when you use that kind of canonical anti-commutation relation. So we'll come back and talk about this again when we go to QFT and start building it up. And then we introduce this anti-commutation relation once again and see how that leads to totally antisymmetric wave function right away. But you spotted it, and that's the answer you're going to get. Does that answer your question, Meryl, for now?
Yes, thank you. That's super helpful.
Okay, great. Any further questions at this stage? Is that okay? All right. So I'd like to also give you a couple of interesting facts about the harmonic oscillator you may or may not have seen in quantum mechanics class. So quantum mechanics is all about uncertainty principle, right? The X is never certain unless you're an eigenstate. P is never certain unless you're an eigenstate. And you can never have a simultaneous eigenstate of X and P. There's always minimum uncertainty about the product of how uncertain the X is and uncertain P is. And the product delta X times delta P is always equal to or greater than h bar over 2. That's what you learn in quantum mechanics class. So now I have another poll. So when you think about the number state, that's the energy eigenstate of the harmonic oscillator. Let's see. Here we go. Here's the pole. So you have this number eigenstate n. And think about n ranges all the way from 0 for the ground state to a much bigger number, like maybe a million. So which state is more uncertain? Bigger n is more certain or less uncertain or the same? So you might come up with the arguments. Large n is supposed to start approaching classical physics. So that sounds like the larger n state is more certain and therefore uncertainty is less. That's one possible answer. On the other hand, when n is bigger, x and p becomes bigger, and we're talking about delta x and delta p, so that looks like it's going to get bigger. Or maybe both of these things would balance against each other and the uncertainty would stay the same. So that's the pole. So if you go to large n in harmonic oscillator, does the uncertainty grow, decrease, or stays the same? Again, this doesn't count towards your grade, so feel free to choose make any pick. Good. All right. About a third more to go. Interesting. Okay. I think one more person. Okay, I guess that's it. Here we go. Share the result. So that's what you chose. So 4 people said, as you make n bigger, it approaches classical mechanics and state becomes less uncertain. 6 of you chose that if you go to larger n, x and p are bigger, so naturally uncertainty is bigger. 11 of you chose, well, these things precisely balance against each other, uncertainty remains the same, it's always h over 2. All right, so we will see which one is the right answer. So we work it out. So for the simplicity of algebra, I take the unit where all these parameters are 1, m, omega, h bar are 1. And that makes things very simple because if you look at this expression for annihilation operator, you take m to 1, omega to 1, h bar to 1. So that simplifies to just x minus ip over square root 2. That looks a lot simpler. So we can deal with that. So the first thing you need to do is to compute the expectation values of both x and p following the definition of what uncertainty is. So plugging in x in n state, x is now written as a plus a dagger over square root 2. A acting on n bring you down to n minus 1, that's orthogonal to n, so that vanishes. A dagger acting on n would bring you up to n minus 1, that's orthogonal to n, so that vanishes too. So x expectation value is exactly 0. And same goes with p expectation value, which is nothing but a minus a dagger over square root 2 times I. The same argument, the same result, 0. What doesn't vanish though is the expectation value of x squared. So now x is a plus a dagger over square root 2. You square that, you get a plus a dagger squared over 2. And in the a plus a dagger squared, a piece vanishes because that will bring n state 2 notches down to n minus 2, that's orthogonal to n. A dagger vanishes too because that would bring the state n 2 notches up to n plus 2 state, that's orthogonal to n. But the cross terms do not vanish, a dagger and a dagger a. Because a dagger a would bring n down not 1 notch and bring you up 1 notch, so stays n. And actually, a dagger a is nothing but the number operator, so that gives you number n. There's a 1/2 in front, so that piece is n over 2. A dagger is not quite a number operator, right? So I can change it to number operator by interchanging the order between a and a dagger. So I write a dagger as a dagger minus a dagger a plus a dagger a. So a dagger a cancels between them, so a dagger stays. But writing that way, a dagger minus a dagger a is nothing but the commutator a dagger plus a dagger a. And a dagger a is now number operator, that pulls out another n with a half in front. So n over 2 we had before, n over 2 we got now, add up to just n. But I'm still left with commutator. But you know commutator is 1 times 1/2 sandwiched between n state, so that's this contribution 1/2 coming out of this commutator. So end result is very simple. X squared expectation value is n plus 1/2. I go through the same thing for p squared. And again, I get n plus 1/2. And you're going to go do this yourself in a homework problem. So this slide tells you how to do it, and you do it yourself. Now we have an answer. So definition of delta x squared is x squared expectation value minus x expectation value squared. That's the usual definition of what is called dispersion in statistics. So you take the expectation value of x squared, you take the expectation of x and you square it and subtract it, and that's a definition of uncertainty delta x squared. So in our case, x squared expectation value is n plus 1/2. You subtract x expectation value squared, which is 0. So the end result is that delta x squared is just n plus 1/2. Same for p. Delta p squared is defined as p squared expectation value minus p expectation value squared, and second term vanishes. So it's nothing but p squared expectation value, that's n plus 1/2. So the total uncertainty here is that delta x squared is n plus 1/2, delta p squared is n plus 1/2, and the product is n plus 1/2 squared. And what we learn as uncertainty principle is that delta x delta p is always bigger than h over 2. Because we're talking about the square of the whole thing, this has to be bigger than h over 2 squared. Remember, we took the unit where h bar is 1. So the minimum uncertainty h over 2 squared is 1/2 squared in this unit. And lo and behold, when you take n to be 0, that's the ground state, you saturate this inequality 1/2 squared. So the ground state is the minimum uncertainty state. It has the least uncertainty as allowed by the uncertainty principle by Heisenberg. That's the smallest it can get. But if you go to large n, even though large n should start mimicking more classical behavior, it becomes actually more uncertain. So that's the answer to this quiz. Larger the n is, the state is actually more uncertain, which is a little bit surprising. When you go to larger and larger n, normally you would think that the uncertainty due to quantum mechanics becomes less important because now you're talking about the macroscopic motion. So what we learn here is that number state is not quite what we imagine for a classical motion of the pendulum. There must be some better state that would mimic the classical motion of the pendulum with the minimum uncertainty that becomes more and more negligible as you go to larger and larger amplitude. So we should look for such a state, which is not the number state, some different state, but that has minimum uncertainty allowed by Heisenberg, so that we don't get scolded by Mr. Heisenberg, and yet mimics the classical motion with large energies. Number state is not it. It must be something different. Okay, any questions about this slide? So on the next slide, we start looking for such a state called the coherent state. Okay, I don't see any questions. Okay, so larger uncertainty for larger n is something, I would personally be surprised by. But we get intuition on what's going on here. So if you think about the classical motion of a pendulum, what it does is this, right? Think about x and p plane. Classical particle has very precisely defined x and p, you can know x and p with infinite precision at the same time. So it's just a point on this plane. And as pendulum swings back and forth, x goes from positive to negative and back to positive. And as x decreases, momentum picks up. So that's how this circular motion appears on x and p plane. If you start where this circle crosses the positive x-axis, that's when you bring the pendulum up this way. And when you release your hand, x starts to decrease and falls down, and p starts to pick up in negative direction. So you go down to the lower half plane, and eventually the position comes to the minimum, and you get the maximum momentum in the negative direction. That's this bottom end of this circle. And you keep going because it did pick up momentum and starts to climb up the hill, and eventually comes to the maximum x in the negative direction, and it stops there, namely zero, momentum is zero at that point. That's the left end of this circle. Then starts roll down the hill again, now picks up the momentum in a positive direction, and eventually comes back to where you started with. So that's the circular motion on XP plane, and that's what harmonic oscillator does. And classical motion is just a point on this circle. If you go to quantum mechanics with fixed energy, that's what the number state is about, then you need to maintain x squared plus p squared to be a given number. But as we learned in quantum mechanics, n goes only by step of 1. So there's nothing between n and n plus 1. There's no energy of 10.4 or 3.14. So what that means is that number eigenstate basically covers from n plus n1, n plus 1. So quantum mechanics makes everything fuzzy. We have the fixed energy, meaning that you want to fix the radii from the 0. That's the energy given by half x plus p squared. But it's a little bit fuzzy. So the number eigenstate would correspond to something like this intuitively. But with this, you can see right away that expectation value of x vanishes, as we saw in the previous slide, because if you take the average of x using this circle, that averages out to 0. So the quantum eigenstate of Hamiltonian with number eigenstate is basically sort of the time average of this classical motion given as a snapshot. Your quantum state experiences every part of this circle all at once. And that's how the state becomes stationary. It doesn't move. And that's the definition of the stationary state. So intuitive understanding of what's going on with the energy eigenstate in quantum system is that time averaging in classical mechanics is done all at once. Your particle occupies every stage of this time evolution in classical mechanics at any given moment. So it's spread out along this circle at any given moment. That's why expectation value of x just vanishes. Expectation value of p just vanishes. But along this circle, when you compute expectation value of x squared and p squared, that's a big number now away from 0. So indeed, x plus p squared is order n, and that's nothing but the energy. So here I see that it's somewhere between n and n plus 1. What we computed in the previous slide explicitly is exactly in the middle, n plus 1/2. So this intuitive picture actually makes sense even quantitatively. So that's what the number eigenstate is. And because it occupies every stage of this classical motion at once, it doesn't mimic what we think of swinging pendulum of a harmonic oscillator. So what we really like is a state that looks something like this, right? So I'm sorry, these equations what we verified on a previous slide. I'm not going to repeat this. But what the state we would like to have is something like this. The size of this circle is the same as the circle for the ground state that's shown in red in the middle picture. That's the ground state. And that's our minimum uncertainty. We keep the same area to make sure that's the minimum uncertainty. But we put this minimum area on top of this circle so that it now has well-defined motion to go around this circle. That will be the state that will mimic the classical swinging pendulum the most, which still doesn't make Mr. Heisenberg mad, because I made sure to satisfy the minimum uncertainty, there is this area. But now we can move along this circle. And that is exactly what is called the coherent state. So at any given moment, x is approximately x naught, p is approximately p naught, and the range is only between 0 and 1, that corresponds to minimum uncertainty. And see if you can get a state like this, which is called the coherent state. So I'm just about to run out of time, so let me just flash you that such a state does exist. And we're going to actually show that coherent state ends up being an eigenstate of the annihilation operator. You might say, huh? Because you always talk about eigenstates of Hermitian operators, and eigenvalues are real. Like Hamiltonian being a Hermitian operator, its eigenvalue energy is a real number. Annihilation operator is not a Hermitian operator. It turns out the eigenvalue is not a real number either. We're talking about a complex number as the eigenvalue. But because f is a complex number and a is written as x minus ip, once you have this complex eigenvalue f, you know its real part and imaginary part at the same time, as if you know x and p at the same time as a real part, imaginary part. This is what mimics this little circle on this big circle with a minimum uncertainty, because you somehow know x and p at the same time. Of course, I shouldn't make Mr. Heisenberg mad, so there is definitely uncertainty associated with it. We're going to see and work it out explicitly on next Wednesday. But nonetheless, this is the kind of state we're looking for when you want to see how harmonic oscillator mimics a classical pendulum. And the reason why we talk about this is when we actually start talking about laser in quantum field theory. Laser mimics classical electromagnetic wave very accurately. And the way you describe laser in quantum field theory actually uses this coherent state. That's why I'm talking about this with harmonic oscillator first, so that we can get to use it later on. So I stop here, and we will talk about this coherent state anew on Wednesday. But in any case, this is what we talked about today. And the intuition, I hope this picture makes sense, that an energy eigenstate is not what really looks like the classical pendulum, but we are looking for something different here. Okay, I stop here. Are there any questions? Come on, I'm sure you got questions. No?
Oh, well, this is not on the material, but you said you sent out a poll for office hours earlier.
Right, Doodle, yeah.
Yeah.
Well, yeah. So not everybody actually has cast a ballot yet. So I have something like only 17 people who cast ballot on the Doodle poll, and not everybody. So I'd like to still wait just a little bit more. Hopefully, all of you would fill out the Doodle poll over the weekend, so that I can announce the office hour at the beginning of the week, so that I wouldn't miss it the next week. So please do that. Any further questions? Everybody happy? Okay, so once again, I'm going to make fix the typos and convert the slides in PDF, post that on B courses, and also convert the video and upload on YouTube so you can watch it later if you like to. All right, so have a good weekend. See you on Wednesday.